Hello and welcome to segment 4. So in this segment we will talk about XLA compiler, and this compiler will help us in optimizing the workflow that we will write in TensorFlow, and some demonstrations also we will see. So XLA is accelerated linear algebra. As you can see from this name itself, this has all these different optimization algorithms for mostly started with linear algebra. Obviously this will be used for all these machine learning and AI algorithms which are mostly used as domain specific compiler for linear algebra and designated designed to accelerate the TensorFlow models. Now this was developed by Google and integrated into TensorFlow, XACS and PyTorch as well. So in the PyTorch we have not used XLA as explicitly as we will see in this TensorFlow, because this is well integrated into TensorFlow, and this compiles TensorFlow computation graphs into optimized machine codes for target hardware, be it CPU, be it TPU, be it the GPU, wide varieties of GPU that we see from NVIDIA as well as other vendors. So this compiles the TensorFlow code or the computation graphs into optimized codes. It was actually started to launch these TensorFlow operations into your standard GPU execution, because TensorFlow was earlier introduced by Google and they wanted to separate the CUDA kernels from the TensorFlow compilation complete stack. So you see why it was created, and obviously over the time the compiler has its advantages and evolution, and it incurs some overhead. Obviously when we are talking about the TensorFlow, we should talk about the XLA compiler with the overhead that will come with the kernel launch latency plus the intermediate memory reads and writes, which is common for every kernel launch runtimes you see. XLA fuses many operations into single kernel. It has less overhead and better utilization, because in this TensorFlow we have seen that each operation that you define under this tf.function decorator, it will be converted into this TensorFlow graph, which will be cached based on an input signature that you define, and when that input signature matches, it will take the graph from the cache and basically it will execute it. However, while defining this graph, we have exactly the same operations that we write in the Python, right? So if it is multiplication, addition or whatever, but then the XLA compiler comes into picture and basically they fuse the operations. It reduces memory overhead by several optimizations. So in the front end, what is happening? In the front end, your graph is getting compiled. Basically it will generate the intermediate representation. In the optimization stage, it will do the optimizations like fusion, then the dead code optimization, then different data dependency optimizations and so on and so forth. So all these things will happen in the middle, and in the back end it will generate the codes for your target GPU, CPU or tensor processing unit for that matter. So it supports all these different targets, CPU, GPU, TPU. The primary target was GPU. Entire TPU execution is actually based on XLA. So that's why it is kind of different from the CUDA kernel based execution, while you see for the GPUs. So CPUs, so it generates optimized LLVM IR for x86 ARM processors. GPUs, for the GPUs it will generate optimized CUDA code for NVIDIA GPUs, PTX code as well, and for TPUs this is the primary target, as I have said, and obviously it has additional support for AMD ROCm GPUs. As I said, it supports multiple GPUs from multiple vendors, so it has support also for the AMD based GPUs, which is mostly experimental, but things are getting there. XLA versus standard TF execution is bit different. So standard one TensorFlow operation equal to 1 kernel launch per operation in standard, but in XLA it fuses multiple operations into one kernel and then it launches, which reduces the kernel launch time also. Okay. So, you are talking about the fusion, right. So, fusion of the execution values. So, you can see here before XLA, let us imagine I have the same ReLU which is applied on the matrix multiplication plus the bias addition value. So, that means matrix multiplication will generate one set of temporary tensors and then which will be used inside your bias add and which will be used in your ReLU computation. So, these are the 3 stages of that computation that we have seen, but in this XLA compilation it improves the execution by operator fusion. So, here is an example of operator fusion. So, each operation will not be called and invoked every time, where these temporary variables will be stored and again they need to be fetched from the memory to create or to have the next kernel launch. Okay. So, here this fused kernel, which is basically happening by fusing the matrix multiplication, bias addition and ReLU, and you will have fewer launches and less memory overhead or traffic. So, XLA or the extended linear algebra compilation often helps by reducing intermediate tensors. As I said, intermediate temporary tensors will be reduced and it will combine multiple operations into optimized block, which will reduce the kernel launch as well as intermediate memory storage. So, this is how the XLA works. Now, as I said, in the front end you are generating the intermediate representation. For any modern compilation flow, usually these 3 stages are there. One is front end, another is back end, and middle you have the all sorts of optimization based on the target that you are compiling for. Now, in this step we create this high level optimizer or HLOIR, which is widely used for TensorFlow and TensorFlow kind of framework, where TF graph is converted into high level operators or operations representation, and this representation is basically used in the optimization. So, this is a simple hardware agnostic means it is not dependent on any hardware optimization, but it is basically an intermediate representation which is defining the operations in the graph, in this dots or convolutions or the reshapes or the reduce or add, this type of operations. Okay. So, basically these operations are the HLO operations, or the intermediate representations are defining a set of operations, and those operations that you define in the Python, they will be converted, or in the graph they will be converted into these HLO operations, which will be used in the second stage, which is the graph level optimizer. And here the algebraic simplification will happen, which will remove the redundant data, and then operation fusion will happen based on obviously what are the tensors that, if you have very huge kernel with the huge or data chunks, it will tile. So, many such different optimizations are there, tiling, chopping and fusing different operations. So, it will merge element wise and broadcast operations into single kernel. So, that way it will do the fusion, and then the layout assignment will happen based on, as I said, that it will do several tiling, chopping and reshaping of the tensors that is coming into the kernels, and it will define memory layout for NHWC, which is versus NCHW. So, it has just kept the total amount of data same, but it has reorganized the different dimensions here. So, these things happen in the middle or the optimization stage or step 2. In the step 3, in the back end the code generation happens. As I said, for the CPU it emits LLVM-IR, because the CPUs will be using, or CPU compilation will be using the LLVM-IR, which will then compile to the native code of the target processor, be it x86 or ARM, and it will emit CUDA based on if I have the GPU target, and for the TPU it generate TPU specific binary via tensor cores instructions, and that way it supports all these different targets for your backend code generation. So this is a compilation flow, domain specific compilation flow, and basically several optimizations that we have seen. So without fusion, this is an example. Convolution will write to a high bandwidth memory, and then again ReLU will read from a high bandwidth memory and write it back. But with fusion, the convolution and ReLU will execute at the same time, and basically it will be storing the intermediate results in the registers, and there will be no HBM transfer. So that means it will reduce the memory operations, which will reduce the energy consumption as well. Okay. So that's how the XLA works, and to enable the XLA we can use JIT compilation 2, which is basically the runtime compilation, which is very fast as well. So this is how this compilation happens. So if I have the decorator as tf.function, and we can do this JIT compilation equal to true, so then it will actually generate the or invoke the XLA compilation and go through this optimization process that we have just talked about. And then in the method 2, we can set the tf XLA flag equal to auto JIT 2. So this will be basically for global setup. So this will not be applicable for any function as such. It will be a global setup. For the method 3, Keras compilation with JIT compile is also possible. So model.compile, when we do call the Keras API, so we can do JIT compilation true that in that particular time also, and XLA compilation will be invoked at that point of time. What XLA cannot compile, compilation will not happen for dynamic shapes where sizes can change in the runtime, because it will use the static shapes. Other than that, the optimization will not happen, because if we do not optimize, then XLA invoking is not required. And Python control flow dependent on tensor values also will not be compiled. So that's why we use tf.cond instant, right? Python control flow will not be working here. And custom operations with XLA kernel implementations are there, which actually uses the XLA compilation flow. Okay. So you can have different setup. So we'll go directly to the setup and basically try to see the code section and try to understand how it can be invoked. But before that, we'll talk about the full training custom loop, which is using that tf.function, right? So in the previous segment, we have seen what? We have seen how to set up the signatures as well as the autograph concept, right? Autograph concept, that was important. And here this build CNN is the CNN build, and you can see that we are invoking few off the shelf Keras layers, convolution 2D, then max pool, then again convolution, then the global average pooling, then the dense dropout and dense. So you have the layers defined, and the model is now defined with build CNN. So the model object has been created, and then we are actually running the optimizer. The loss function is computed, and then the function that is doing the training step that we are defining here. So training step is taking the batches, okay, the data and the labels, and this is defining with the gradient tape. So from the segment 1 and 2, you can understand why we have the gradient tape here, which will track the gradients for these operations. And then we are actually invoking this gradient method to calculate the gradient of loss with respect to all these trainable variables, and then we are applying optimizer, then we are returning the loss. So this is basically my training loop, right? And this is defined under this function decorator, and this is the evaluation. So it's almost same, only this training equal to false, so that the dropout and batch normalization will not happen. This is same as PyTorch. Now here we are having some synthetic data. I am not going in deep word details. And then the validation set and the training data set has been created, and then the final epochs are running the training step, right. So, this is the training step function that has been created, and each epoch for all the data we are actually batch by batch running the forward pass and calculating the loss in the backward pass. Good. So, now this is the complete training pipeline, and you can see we have the evaluation step and the training step, which is repeatedly called, right. So, training step is repeatedly called with this X batch and Y batch. So, what we should do? We should keep it in the graph, right. We should cache this particular step. So, that is what exactly we are doing it here. Obviously, rest of the training process that you can follow. Now, when we do the TensorFlow's optimizer fold at the compilation time, we can do this with constant flow fold, which will fold this, right. So, this is one operator fusion that we are doing manually, and we can also do by XLA. Okay. So, this training step, what we have seen, obviously now the training step or training loop is not important here, rather we are trying to see the operations that we are executing, whether they are fused or not, based on the XLA compiler, or we are using without XLA compiler. Okay. So, now here you can see we have this convolution 2D and the bias addition and then the ReLU. The same graph we have talked about, convolution 2D, then the bias add, then the ReLU activation. The same thing we are doing where we are using this unfused operation. So, that means what is the difference here? Here obviously when we are calling this fused operation and an unfused operation, what is the runtime that we are trying to measure? For this simple use case, it will not show the performance gap, but the usage is clear here, how to use this basically. Okay. Okay. So, now in this function, one thing is that we are activating the XLA compilation by using JIT compile equal to true, and here we are switching off the XLA compilation by using JIT compilation equal to false. So, now you can see that how you can reuse that for your training step. The entire training loop that we have defined, the training loop, you know, the per epoch, per batch, you have the loop, and basically function which is under this tf dot function, whether that function will use this fused operation or not, that will be defined by this particular argument here. And then running that, we can see that this unfused will take this much time, XLA fused will take this much time, and for this particular segment, which is very basic computation, right, you have the convolution, you have the bias addition, and then you have the ReLU activation. These are three stages that we are running. Without fused operation, what we are doing is that we are taking out the tensors and using the memory. Again, from the memory we are taking it and using it in the bias add, again storing it, again using it and giving it to the ReLU, and that is how it is happening. Obviously, there will be a few bit optimization than that, very naive way of saying it, but you got the idea. When you fuse, all these operations are happening inside the registers, and basically for this simple fusion of operations, we are getting around 1.42 times speed up. Okay. So, this is a very basic optimization that you can apply for your TensorFlow graph formulation. So, TensorFlow graph formulation we can do, TensorFlow graph formulation we can cache it, and we can use actually input signatures from the graph definition to use cached graph. So, compilation will not happen again and again, retracing will not happen. So, or rather tracing will not happen again and again per function call, right. That is exactly what this training step will do. for each epoch or for each batch, it will actually fetch that particular training step, which will do the forward pass, which will calculate the loss function, which will do the backward pass, which will update the gradient, and then it will update the weights as well. So now in this XLA compilation, we can further improve that by using fused operation wherever it is applicable for this particular target. And this is exactly what we have seen now. Okay. So with this, we will conclude this segment, and in the upcoming segment, we will see a few more optimizations with mixed precision as we have seen in the PyTorch segment. So PyTorch segment in detail, we have seen different data types with 64 bits, double precision, single precision 32 bit, 16 bits, TensorFlow 16 bits and floating point 16 bits. We have seen 8 bits as well as integers with 4 bits. So we have seen many different data types. Now in TensorFlow also, obviously TensorFlow TF16 will be widely used. However, we can also use mixed precision here to improve the performance further, okay, as well as some other optimizations we will talk about. And also one more important thing that we will discuss in the upcoming segment, which is interoperability, which is going to be very important when we come to the deployment segment. We will discuss in detail. Thank you here.